Today, we're diving into Sa2VA, a superhero fusion of SAM2 and LLaVA, combining segmentation and vision language capabilities. Unlike traditional approaches that treat these as separate tasks, Sa2VA unites them through a single instruction tuning process. This enables it to chat about a photo, caption a video, and pinpoint objects, all in one go. Let's dive in.
Let's start our journey by imagining a tool that can look at images and videos and understand them in remarkable detail. Picture a bustling city street at night, where someone is walking with dazzling streetlights in the background. This person is holding a handbag, wearing sunglasses, and blending right into the scene. Now, what if the model you're looking at could not only describe the streetlights and the trendy handbag, but also answer specific questions about the person's outfit or isolate the person in the scene? That's exactly what happens here. The model grounds its visual analysis with textual explanations and precise segmentation, smoothly linking vision and language. It's like it can both see and explain at the same time, bridging that gap in a natural way. Ready to move on? Let's explore more examples. In this next part, we dive deeper into the model's capabilities. It can handle tasks like captioning images and videos, answering questions in a conversational manner, and segmenting objects based on a user's instructions. Curious how it works? Check out the radar plot here, which compares Sa2VA to other models across multiple benchmarks. You'll see it standing out in segmentation, video conversations, and various multimodal tasks. Want a glimpse of what it does? It can describe a snowboarding scene with details about the snowboarder's gear, answer what a giraffe is doing in a photo, or even isolate a person wearing a specific outfit in a video. And it does all this through a unified approach that merges understanding and segmentation for both images and videos. It's tuned with just one set of instructions, making it streamlined and efficient. Next, let's talk about how Sa2VA brings together two powerful models: SAM2, which specializes in video segmentation, and LLaVA, a vision language model. By merging these, Sa2VA creates a system that can navigate text, images, and videos in a shared token space. In practical terms, it can use language instructions to guide the segmentation process, producing masks that pinpoint the exact objects of interest in both images and videos. Take a moment to look at the details about the RefSav dataset. It has over 72,000 object expressions in various videos, training the model to handle complex scenarios. This paves the way for strong results in tasks like referring video object segmentation. The paper also highlights three big challenges: how to formulate tasks, how to ensure a balance between language and visual performance, and how to unify knowledge across different models. Here, we focus on the challenges of fine-grained video understanding. Why is it so tricky? Because we need to segment and track every pixel while also making sense of language prompts and responding to visual questions. Many current models can do one thing, like segmentation or basic language tasks, but not both in a single framework. Sa2VA addresses this by partially freezing components of SAM2, such as the decoder. That way, the strong perceptual features remain intact, but it still gets aligned with the language components. And there's the RefSav dataset again, packed with complex video scenes that put Sa2VA to the test. By training on both image and video data, the model avoids the need for different systems for each task, making it more flexible and scalable. Now let's see how Sa2VA stacks up against other leading models. If you look at the comparison table here, you'll notice Sa2VA handles images, videos, and text prompts all in one place. It supports dense grounding and conversations, unlike some models that only handle a limited range of tasks. When tested on 6 different benchmarks for image and video segmentation, it achieves leading results, especially on the tough RefSav dataset. The performance gains over 15% in zero-shot scenarios show how well this unified approach works. The discussion also underscores how having better data sources and unified formats can push multimodal language models forward. Let's look at the novel contributions Sa2VA brings. First, it merges SAM2 and LLaVA-like systems, making it capable of handling spatial and temporal data in one framework. That means it can reason about both images and videos in a grounded way. The key idea is a shared segmentation token that keeps things modular but still interconnected. Another highlight is the RefSav dataset, built for referring video object segmentation. It includes scenarios with occlusions, motion blur, and long text descriptions. The authors went the extra mile by manually verifying thousands of these samples. The related work section contrasts this approach with previous efforts that often focused on a single task, like segmentation or captioning. Sa2VA stands out by integrating conversation and segmentation together in videos, a step toward more holistic vision and language understanding. Moving on, we see how Sa2VA pushes the envelope in video segmentation and grounding. It supports interactive chat alongside video understanding, tackling issues like spatial temporal modeling and the lack of broad training data. Many current models aren't as flexible, especially with open-ended tasks like video question answering or grounded understanding. Sa2VA fills this gap by offering a single system that can handle a variety of tasks. Its methodology starts with unifying how different tasks are represented. Whether it's image segmentation or video conversation, everything follows one standardized pipeline. Text inputs guide the creation of precise visual masks, enabling interactive and grounded understanding. At the heart of it is the Sa2VA framework, which uses pre-trained backbones alongside SAM2. Together, they process different inputs, images, videos, or sub-images, and produce outputs that can be used for captioning, segmentation, or conversations. What tasks can Sa2VA handle? It ranges from image or video chat to grounded captioning. The system takes your text prompt, along with the image or video, and responds with text or a segmentation mask that aligns with what you asked for. Under the hood, it uses a single instruction tuning process that keeps everything consistent. A key feature is its decoupled design. That means SAM2 and the LLaVA model can plug right into each other with minimal fuss, thanks to a special token. This token lets SAM2 refine its segmentation based on language prompts. Gradients can flow between them during training, so they learn to collaborate effectively. When it comes to actually tracking the segmentation across frames, SAM2 uses its existing knowledge to produce reliable results. By combining these approaches, Sa2VA delivers competitive performance in public benchmarks without needing separate, specialized tweaks for each task. Now let's break down the Sa2VA architecture. First, the input, whether text, an image, or a video, is turned into embeddings. These embeddings feed into a large language model, where features from different modalities are blended. The output includes both traditional language tokens and a special token. This token helps generate accurate segmentation masks that match the prompt. Next up is the SAM2 decoder. It takes the visual features from SAM2's encoder plus the token to produce segmentations for images and videos. You can see it outputting results like referring segmentations, grounded captions, or even answers to visual questions. This modular design means the system can handle a wide array of tasks while remaining accurate and easy to adapt. At the bottom, there's a data annotation pipeline mentioned for video frames. It starts with cropped images for objects, then carefully refines them to create part-level descriptions. This setup helps the model excel in multiple tasks at once. Here we get more details on the RefSav dataset and how it's annotated. The pipeline follows 3 steps. First, there's object or part-level annotation, so each element is identified. Then, scene-level annotation captures how that element fits into the overall setting. Finally, video-level annotation considers the entire sequence of frames, delivering a full context of how objects move or change over time. Because of this careful annotation process, RefSav ends up with 37,000 plus videos and more than 72,000 object expressions, each uniquely described. For testing, they use a separate set of videos with no overlap from training to ensure fair evaluation. This means the benchmark is robust and unbiased, letting us truly measure how well Sa2VA performs under real conditions. Let's check out some experimental results now. If you look at the table here, you'll see how Sa2VA measures up in tasks like image and video segmentation, image chat, video chat, and more. They split the dataset into a long expression set and a short expression set. The long expression set is automatically annotated, while the short expression set is manually curated. This gives a good balance between variety and accuracy. Sa2VA is co-trained on multiple datasets, including benchmarks like RefCoco and MIVIS. It uses the hidden state of the token to decode through SAM2's layers, yielding precise object masks and context-aware results. That's why it performs so well in these multimodal tasks. Now we move to training and testing details. Sa2VA uses text regression for language tasks and a dual loss technique for segmentation, giving it both high-level context and pixel-level accuracy. Everything is unified into one framework for testing, whether it's segmentation or text generation. When you feed prompts, images, or videos, Sa2VA turns them into tokens. Then, it outputs either text, segmentation masks, or video results. Diverse datasets, from image QA to video segmentation, were used to strengthen the model. Evaluation metrics like IOU and J and F confirm that Sa2VA outperforms previous models, especially when the tasks require a tight integration of text and video understanding. Here we see how Sa2VA fares on standard benchmarks like RefCoco and RefCoco-G. It shows strong results across both image-level and video-level tasks. For referring segmentation specifically, Sa2VA leads in both zero-shot and fine-tuned settings, indicating it can handle intricate queries. The training approach involves fine-tuning the language model with carefully designed prompts, while segmentation losses make sure the pixel-level details aren't overlooked. They use large-scale hardware and enormous datasets, spanning millions of examples across images and videos. With these resources, Sa2VA achieves consistent improvements over competing methods, managing everything from segmentations to conversations. Next, you'll see a comparison of Sa2VA to other top-tier multimodal language models. In image and video tasks, it achieves new records on datasets like RefCoco and RefCoco-G. It also does well on video-specific challenges, including segmentation and video question answering. That means it's covering a wide spectrum of modalities. If you're curious about the RefSav dataset specifically, you'll see that Sa2VA handles tough scenarios like occlusions and long descriptions effectively. Fine-tuned versions keep outperforming other models on multiple benchmarks. This success is partly due to its co-training strategy, which tackles different tasks simultaneously under one umbrella. They even include ablation studies to show just how crucial this joint training approach is. Here, the paper delves into how joint co-training shapes Sa2VA's success. Removing certain datasets, such as image segmentation data, causes big drops in performance, highlighting the importance of diverse training. They also explore using stronger base models like Intern VL 2.5, and they see even better results, especially in segmentation and image chat tasks. This proves the system can scale effectively. They also offer visual examples to illustrate how Sa2VA can describe scenes in detail, blending textual and visual elements. It can point out specific objects and then explain their context in simple language. This blend of text, image, and video is the core of what makes Sa2VA special in multimodal tasks. In this part, we see more ablation studies and scalability tests. Joint co-training with multiple datasets boosts performance in video segmentation and quality assessments. Different strategies for the token are tested, each with pros and cons regarding segmentation precision and knowledge sharing. When they add extra datasets, like 3 million image QA examples, Sa2VA's scores improve in various benchmarks without losing ground elsewhere. If you check out the visualization examples from RefSav, you'll notice complex situations with occlusion, reappearance, and different text lengths. This dataset is tough, and Sa2VA's ability to handle it underscores its unified design. That design bridges text, images, and videos under one system, showing adaptability across many tasks. Finally, the paper discusses more ablation studies and comparisons that highlight Sa2VA's strengths. They test different token designs, single, repeated, or multiple, and analyze how each affects segmentation accuracy. The multiple strategy strikes a good balance between performance and lower error rates. They also examine how adding extra training data, whether it's more image QA or more video samples, consistently raises Sa2VA's scores on multiple benchmarks without harming existing capabilities. If you compare it to models like UniRef or LPMM, you'll see Sa2VA competing strongly in both video and image tasks. The validation tests confirm improvements in region captioning and object segmentation, reinforcing the model's robustness. And that brings us to a close on how Sa2VA unifies vision and language, tackling a variety of tasks in one neat framework. One way to think about Sa2VA is seeing how it turns what we see into what we can say, and then turns what we say into what we can see. Thanks for joining us, and we'll see you tomorrow.